In this video, I want to show you a confidence interval for the median difference. In this video series, we've studied several two-sample methods and have seen how these fit into a general framework. We've been focusing on a null hypothesis about the equality of medians in two independent samples. A confidence interval can provide more information than a single hypothesis test, so it is now time to turn our attention to confidence interval construction. The only package required to follow along with this presentation using R is nplearn. In the series on one-sample methods, we were introduced to a Hodges-Lehmann estimator for the median of different scores. I'm going to again use a Hodges-Lehmann estimator, but this time a different one. This is for the median difference with two independent samples. Let d sub ij equal x sub i1 minus x sub j2. Now what are those? X sub i1 is a score from the first sample, and x sub j2 is a score from the second sample. D is simply the difference between those. In other words, D is the difference between a score from the first sample and a score from the second sample. We're going to calculate all these differences. That is, we are going to vary I from 1 to the size of the first sample, and we are going to vary j from 1 to the size of the second sample. In so doing, we will capture all possible differences between a score in the first sample and a score in the second sample. The Hodges-Lehmann median difference estimator is going to be the median of these differences. This theta hat sub d estimates a population value of d. That is, if we had taken differences in the population instead of our samples and calculated the median of all possible differences, that would be theta sub d. We are going to look at theta hat sub d because we're using our samples, obviously, instead of the populations. In this video series, I've been using an example from reading instruction in which we compare prosodic reading instruction to repeated reading. What we're primarily focusing on is the number of errors that students make when they read after receiving these kinds of instruction. We expect that in the prosodic reading condition, they will make fewer errors. At least that's the research hypothesis. So we set up the scores for the prosodic condition, and we set up the scores for the repeated reading condition. Now what I'm going to do here in this little loop is I am going to calculate all possible differences. So this is the key part here on line 7. I am creating a vector of differences where I take all of the scores from the prosodic group and all of the scores from the repeated reading group. In this case, I was for repeated reading and J was for prosodic. So I'm subtracting a score from the prosodic group from a score in the repeated reading group. Now think about that a moment. If repeated reading is not as effective as prosodic reading, there will be more errors. So the way I'm subtracting here, it doesn't really matter which way we subtract as long as we think it through. The way I'm subtracting here, we're expecting to get larger values of D than if we subtract the other way around. At least that's what our research hypothesis says. So we're now going to look for the Hodges-Lehmann estimator. That's the median of all those differences. And so that's what I'm doing here. We get 7. So theta hat sub d is equal to 7. That's our best estimate. Now remember that if there is no difference in the group, the expectation for theta d is 0. The fact that I got a positive number means that in my sample there is evidence that the prosodic condition is doing better than the repeated reading condition, but I need to know if it's enough evidence to be able to make inferences to the population. Now I'm going to introduce you to a new hypothesis test. You might wonder why I'm stopping in the middle of a confidence interval presentation and providing a new hypothesis test. Bear with me, I'll show you why in a moment. Mann and Whitney independently developed a two-sample test during the same time period when Wilcoxon developed the two-sample test. That is, Mann and Whitney working together developed their test, and Wilcoxon developed his test. The tests use a different statistic, but it turns out that one statistic is a function of the other so that the tests are equivalent. So we actually have two different kinds of tests for two independent samples. In fact, oftentimes when we conduct the hypothesis test, regardless of which method we use, we often will refer to it as the Wilcoxon-Mann-Whitney test, although I think that makes it sound as though the three collaborated together. It's really the Wilcoxon test and the Mann-Whitney test, but let's give them both credit. They developed this at the same time, and you get the same results, but they're done differently. Let's take a look. The null hypothesis here is that the median of the differences, that is, the value that the Hodges-Lehmann estimator is estimating for the population. The Hodges-Lehmann estimator is giving us a sample value, but what would the Hodges-Lehmann estimator be in the population? Under the null hypothesis, it would be 0. That is, when we take those differences, we expect to get just as many negative numbers as we do positive numbers because of no difference in errors in the prosodic and repeated reading conditions, and so we end up with a median of 0. The alternative hypothesis, in the way that I've set it up here, this is why it's important we consider how we subtracted, is that the median of these differences is greater than 0. If I had subtracted the other way around, my hypothesis would be that the median of these differences is less than 0. Notice no hats because we're doing hypotheses about the population. Now define an inversion. That's what they called it for some reason. Define that inversion as a D, that is one of those difference scores, being greater than the median D, that is the median difference, the Hodges-Lehmann value, under the null hypothesis. Well, with the null hypothesis I have here, the conditional theta sub D is just 0. So defining an inversion would be looking for all the positive numbers, looking for values of D that are greater than 0. We calculate U, the number of inversions. This is what Mann-Whitney called it, U, and it's the Mann-Whitney U test. We construct a rejection region such that the probability of U being greater than or equal to a critical value is less than or equal to alpha, as we always do in order to control our type 1 error rate. Now for the confidence interval, we are going to invert that test. We are going to test that theta D equals H for all H, not just 0. We're going to plug in different values for H, and then those values that we retain will form a confidence interval. Now here's the functional equivalency that I mentioned before between the Mann-Whitney U and the Wilcoxon. In the Wilcoxon test, we used a capital T for the test statistic. So the Mann-Whitney U can be found by taking this formula and plugging in a T and the sample sizes if we know the T for the Wilcoxon test. And since you know how to do the Wilcoxon test, that's the approach I'm going to take here. So let's look at this using the example that we have been using with prosodic reading. This is a rank-based test. That means that the Hodges-Lehmann estimator was developed for test of ranks. So instead of the one-sample Wilcoxon, we're now thinking about the Mann-Whitney U, but we're going to start by going back to the one-sample Wilcoxon. So here you can see that I've taken the prosodic and repeated reading scores, combined them, and ranked them after I combine them. Then I'm going to look at all the possible combinations of what t could be as the sum of ranks in the prosodic condition, which only had 4 values in it. So I'm using the prosodic condition as the smallest condition and then calculating up the values of t. Here are all the unique values of t we can get, starting with 10. That would be if we had the ranks 1, 2, 3, 4. And moving all the way up to the highest possibility, which is 30. Now, we actually did this test and we had a t of 11 and we had a p-value of 0.016. I did that in a previous video, so if you've not seen that, you should go back and watch. But what I'm interested in now is the critical value. So there's a couple things I want you to pay attention here before I move on to the next slide. 2 things in particular. 1, how many unique values of t do we have? Well, notice that R has actually given us the numbers here on the side, and you see there are 21. I'm at the very bottom here of the distribution. There are 21 unique values of t. So that's the first thing I want you to keep in mind. The second thing I want you to keep in mind is what the critical value is going to be if we use an alpha of 0.05. So I'm not calculating the p-statistic here, I'm calculating the critical value. The p-statistic we already know is 0.01, about 6. 0.016. So the critical value, I have to go all the way up here as far as I can go without going over 0.05, and I'm already over 0.05 right here. And so this is our critical value. The critical value is 12 when we want to do a test maintaining the type 1 error at 0.05. Ultimately, that means when we want a 95% confidence interval. Okay, now let's consider this in light of the man Whitney U. What is the critical value using U? Well, first I want you to answer this question. What is the range of U? That is, what is the minimum and maximum possible number of inversions? Remember again that an inversion means that those difference scores are going to be above the hypothesized value. The minimum number, of course, is going to be 0. That is, if none of the differences are above the hypothesized value. What's the maximum number we could have? Well, think about that. How many possible difference scores are you going to have? You're going to have the first sample size, that is how many are in the prosodic condition, times the second sample size, how many are in the repeated condition, and that's 20. So the maximum number is 20. We're only using integers because we're talking about a number of inversions. So how many values are there from 0 to 20? We can have from 0 to 20 inversions. That's 21 possibilities. Do you recognize that number? I told you on the last slide to remember it. There are 21 unique possibilities for t, just like there are 21 possibilities for the number of inversions. This is not an accident. It is because of the relationship of t and u, which is a 1-to-1 relationship. If I use the relationship formula and put in the critical value for t, remember that critical value was 12, I'm going to obtain the critical value for u, and I do that with this formula right here. I'm taking the 2 sample sizes, multiplying them together, just like the formula here says. I am taking the smallest sample size, that's prosodic, multiplying it by the smallest sample size plus 1, dividing the whole thing by 2, subtracting 12, and that gives me an 18. Now notice something. When t is small, u will be larger. When t is larger, u will be smaller. So if we're looking at a lower tail with t, it's the same as looking at an upper tail with u. That is, we're looking for a lot of inversions. I need 18 inversions in order to be able to reject the null hypothesis. So let's return to our example with prosodic and repeated reading. We already calculated the differences, so I need to see how many of those differences are greater than 0. That is, how many inversions do I have? I need to have at least 18. That is, I need to have 18 values above 0. I have 19. Just as with the two-sample Wilcoxon test, I can reject the null hypothesis. No surprise, the tests are equivalent. So now you know the Mann-Whitney U-test, but you really didn't need to know that for the purposes of constructing a hypothesis test, because we already had the Wilcoxon test, and the Wilcoxon test gives us the same sort of thing. So let's go to why we use the Mann-Whitney test to form a confidence interval for theta sub d, that is, for Hodges-Lehmann population value. If the Mann-Whitney test is equivalent to the two-sample Wilcoxon, why bother to learn it? The Mann-Whitney version of the test has shown us a relationship to d, the values used for the Hodges-Lehmann estimator. That estimator provides us a sample statistic to indicate the size of our treatment effect, but it also provides us a means to a confidence interval. We test all possible values of theta sub d. Different hypotheses result in different numbers of inversions, and we find all the values of theta sub d that will lead to retention of the null hypothesis. That is, we invert the hypothesis test. In our example, we need 18 inversions to reject the null hypothesis. Here are all the values of d that have been sorted. And I sorted them for a good reason, as we will see. Here's my question to you. What values of theta sub d can we hypothesize to have fewer inversions than 18? Now, we already hypothesized 0. And when we hypothesize 0, we have 19 values that are above 0. Because we have 19 values that are above 0, we're able to reject the null hypothesis. Therefore, 0 will not be in our confidence interval. What about if we hypothesized, let's go to the other end here. What about if we hypothesized a value of theta d of 18? Well, then we only have one inversion. We would not reject. So 18 is going to be in our confidence interval. Now let me go back to the other tail down here, because let's work our way up. What if we hypothesize 1? How many values do we have above 1 here? The answer is 18. Does that reject? Yes, it does. 1 will not be in our confidence interval. What about if we hypothesize a value of 2? Will that reject? No. We have 17 values above 2, 17 inversions, and that is fewer than 18, the critical value. Therefore, we will not reject the null hypothesis. 2 will be in our confidence interval. Let's take it a step further and move in between here. What about if I hypothesized 1.9? Now, 1.9 is not even a possibility here. I'm not actually looking at that degree of precision. But I want to make a point. If we hypothesize 1.9, how many inversions do we have? We would have 18 inversions, 18 values. So 1.9 could be rejected. The boundary, the cutoff point here is that 2. So we've just found the 95% confidence interval. We do not reject for 2 and anything above. So therefore, the measure of my effect size here with 95% confidence is that theta sub d is at least 2. Remember again what theta sub d is. It's the median of d's, where d's are differences between scores in the two conditions. So if I look at the scores in the prosodic condition, I expect the median of the differences between those and scores in the reading condition to be at least 2. 2 here represents a number of errors. So at least 2 fewer errors is what I'm anticipating. This is not a median or a mean of original population values, but a median of all possible differences, which I think gets right to the heart of our research question. We don't have to do all this by hand. I showed you by hand because I believe that it's always good to know how these things work and why they worked, but we can jump right now to an R function. In fact, the Wilcox.test that is in base R actually has a way to do this. All we have to do is turn on the confidence interval. We state here the confidence interval equals true. We could state the level of confidence we want, but the default is going to be 95% confidence. And notice what we get. A 95% confidence interval is 2 and above. The median of differences in the population is at least 2. For a single hypothesis test, which is unnecessary, we know that we would reject. We know that from before because we get a p-value of 0.016. But what does that tell us? It tells us that there is a treatment effect. What does the confidence interval tell us? It tells us how big that treatment effect is, so it provides more information for us. We could also use the R function Wilcox underscore test, which is in the COIN library. That actually will be better for larger samples and when you have ties. But I'm showing you here that regardless of which you use, both have a confidence interval. It's just, in this case, the base R test, if you have ties, it's going to resort to an asymptotic approximation in order to give you that confidence interval. And I prefer using exact as long as I can. Some considerations. The confidence interval for the median difference is not a confidence interval for the difference in medians. You're probably used to the t-test, and in the t-test, the difference in means is equal to the mean difference. But that is not true with medians. The difference in medians is not equal to a median of differences. So the median difference is not a confidence interval for the difference in medians. Nonetheless, it is a valuable effect size measure without taking the difference in population medians. We don't need to do that. When distributions are symmetric, this confidence interval can be used to provide a confidence interval for the difference in means. If we knew the underlying populations in the prosodic and reading condition errors were both symmetric, then the median and means are going to be the same thing. And we could say that the difference in means is at least 2 points. I don't know that you get any more valuable information from this, but for those who are used to working with means, that could be helpful. The Hodges-Lehmann estimator and associated confidence interval are based on ranks. That tells us that this interval is going to be a strong competitor to the t-test confidence interval when we have heavier kurtosis than the normal distribution, a larger kurtosis, more than 3. That is when we have heavier tails than the normal distribution and a higher peak. It's a wider interval than the t-test when we have normal distributions. So if I know that my underlying distributions are normal, I'm going to stick with the t-test. But otherwise, I have a very valuable test, and one in which if I don't know anything about the distributions, I know that my confidence interval will not be too much wider than the t-test even for normality, and in fact could be quite a bit narrower than that for the t-test in other situations.